Okay, so hello everyone. I want to spend today looking at some examples of different kinds of these double integration problems. And mostly what I'm going to do today is just work on setting these things up. I'm not going to spend too much time doing the actual explicit anti-differentiation. That's mostly just cut and dry, do the same kinds of strategies that I've done before. But I want to spend most of today really looking at how to set these things up. Because that's often the more challenging part. And if you do that part correctly and efficiently, then that's going to make the rest of your experience a lot easier. So let's start off with one of these. These are all coming from Stewart, by the way. These are all different even problems in Stewart. So let's start taking the double integral over D. And the region that we want is, the region that we're interested in is going to be y times the square root of x squared minus y squared dA, and D is going to be all x and y, so that x is between 0 and 2, and y is between 0 and x. Now, whenever we're doing any of these kinds of problems, what we should always do is draw the figure. So let's draw what this thing actually looks like. What is our region in this case? Well, x is going from 0 to 2, so let's mark off where 2 is. This isn't to scale, but that's okay. And our region looks something like this. So x is going from 0 to 2, and y is going between 0 and x. So here's the line y equals x. And if x is going from 0 to 2, y is going from 0, I did that backwards. Y is going from 0 up to x. So this is what our figure looks like so far. And in this formulation, it's a type 1 region. So here's D. Now, what that suggests is if you actually do this and you write it out as an iterated integral, this is the integral from 0 to 2, integral from 0 to x of y times root x squared minus y squared dy dx. And that's perfectly fine. Here's what you don't want to do. What I would advise against, because you could also write D, if you want to, this is as a type 1. You could also write it as a type 2 by saying all x and y, so that y is between 0 and 2, and x is between y and 1. Right? If we want to write it as a type 1 region, we would be going this way for x going from y to 1, if you want to write this as a type 1 region. So we can do it that way too. 0 to 2, x to, y to 1, y root x squared minus y squared dx dy. So either of these would work. You can do either of these two integrals. The problem is one of these is going to be much easier than the other. And the problem, and in particular, the issue that's going to come out over here is with this term. So this is the integral from y to 1 of y times root x squared minus y squared dx. And that's a difficult integral because you can't do u substitution because there's no external function. It's just square root of x squared minus y squared. You have to use trig sub for that. You really do need to use a trig substitution. And that's difficult. It's not impossible. One can do it, but it's not ideal. So instead, we're going to use our original strategy, which you can do with u substitution. Specifically, you can say that u is equal to x squared minus y squared, and which would make du equal to negative 2y dy. So now the object becomes 0 to 2 integral of, let's see, if that's u, then that would make 0 to x. That would make u going from, when y is 0, that would be going from x squared to x squared minus x squared, or in other words, 0. Just write in 0 in that case. So of negative 2y, or sorry, that's not what I wanted to say. Negative 1/2 is what I wanted to say. Root u du dx. Which, in other words, is going to now become integral 0 to 2, negative, I believe this would be negative 1/3 u to the 3/2, evaluated from u is x squared to u is 0 dx, or integral 0 to 2 of 1/3 x cubed dx, which comes out, by the way, which I'll just let you know, comes out to 4/3. So that's one way of doing this. Now again, can you use trig sub with the orange integral? Yes, you can. It's just not recommended. There's a much easier way to do it, so I wouldn't recommend trying to do it that way. Okay, let's do another example though. So what if instead, let's consider, hold on a second, I want my pens to work. Okay. Let's consider the double integral over d of the function xy dA, and d is going to be the region enclosed by the quarter circle, and the quarter circle in this case is given by y equals root 1 minus x squared, or x greater than or equal to 0. Now again, always draw the thing first, and in this case if we draw it, what that tells us is that y squared equals 1 minus x squared, or in other words, x squared plus y squared is equal to 1. But that's not the full circle, and it's important to recognize that. It's only the quarter circle, because first of all, this is y equals positive square root, and second of all, you've got x is greater than or equal to 0. So we're only dealing with this piece of it. That's D. For us, that's our region D, right there. So now there are two ways we can do this. We could either, here's the first strategy. You can write D as all points x and y, so that x is between 0 and 1, and y is between 0 and root 1 minus x squared. If that's the case, then this double integral over d is going to become, so it's xy dA, and that becomes the integral from 0 to 1 of the integral from 0 to root 1 minus x squared, xy dy dx. Or, in other words, integral from 0 to 1 of 1/2 x times 1 minus x squared, because you square it, dx. And you do that out, it's not very hard to do that, that comes out to 1/8. So that's one option, but that's not the only way you can do it. Some of you might recognize, wait a minute, that's a quarter circle, why do we use polar coordinates? Sure, you can do that. You could write it as all r and theta, so that you have r going from 0 to 1 and theta going from 0 to pi over 2. Both of these are valid approaches. The polar coordinate approach has the added benefit of having constant bounds. So if you do it this way, this is the double integral over d x y dA, integral from 0 to 1, integral from 0 to pi over 2 of r cosine theta, that's x, r sine theta, that's y, times an extra factor of r, d, actually the way that I've done this, I would have to write a d theta, dr, that's okay, because by Fubini's theorem you can, because these are constant limits of integration, so you can flip these as much as you want. So this could also be the integral from 0 to pi over 2 of the integral from 0 to 1 of r cubed cosine theta sine theta drd theta. And now that's actually a separable integral, so you can write that as the integral from 0 to pi over 2 of cos theta sine theta d theta, integral from 0 to 1 r cubed dr. You can separate it, which is going to become 1/4 r to the 4th from 0 to 1 times 1/2 sine squared theta from 0 to pi over 2. Once again, that's going to be 1/8. So you can do this in either way. These are both valid approaches. Personally, I kind of like the polar coordinate version a bit more because this is a very easy integral to separate, and the algebra is a lot cleaner, I think. But that's a matter of taste. Both of these are perfectly valid ways of approaching this problem. And that's the other thing to be aware of, is that we're reaching the point in our mathematical careers where there are multiple approaches to the correct answer. And you have to decide for yourself which strategy you like more. It's really, as I said, a matter of taste. Let's do another one. What if we want to look at, I don't know, let's say that we want to look at the integral from 0 to 1 of the integral from x squared to 1 of root y sine y dy dx. And I want to calculate that thing. Now, you can do this directly using integration by parts, but that would be difficult. You might even end up running around in circles because this root y, that's not going to have a nice clean antiderivative eventually. You're going to keep on getting these fractional powers, or go in the opposite direction, keep on getting bigger and bigger powers. So doing this in terms of y is not that easy. So this is a difficult it's just difficult to do the antiderivative of root y sine y dy. So we're going to try to find a better way of doing this. And what we're going to do, first of all, same strategy as always, is to draw it first. In this case, we're told that x is going from 0 to 1. Y is going from x squared to 1. So let's draw in the function y equals x squared. Now x is going from 0 to 1. Y is going from x squared up to, so y is going from x squared up to 1, which means that this is our region. This is our region that we're going to be integrating over. It's this fin-looking thing from x squared to 1 for y and 0 to 1 for x. Now, let's say that we want to switch the bounds, or switch the order of integration. And we should do that because, as I just said, root y sine y is a difficult integral to do, bottom line. That's a hard integral. So it would be better for us if we could switch the order of integration. So what's d in this case? Well, d, here's what we know to begin with. We know that it's all x and y. So that, now if we just look for a second at our limits that we've been handed, we know that x is, I'm going to do this in different colors so I can identify where these are coming from. We know that x is going from 0 to 1. We're told that. We're also told that y is going from x squared to 1. But we want to do this in the opposite direction. We want to do this in the opposite direction. We're going to notice that if we're looking at all points x and y, what is y going between? Well, y is also going from 0 to 1. And x is going from what? Well, x is starting, I'll do this one in orange, or I'll do it in green actually. X is starting at 0, but going up to the curve, x equals root y. So in this case, we've got y going from 0 to 1, x going from 0 to root y. By the way, as an aside, I want to point out something. This is, here's what this is not. This is not the following. It is not the region, I'm kind of surprised at myself that I didn't mention this earlier on, but this is not the region of x going from 0 to 1 and y going from 0 to 1. It is not this. Why not? Well, why not? Because you can see that y is going from 0 to 1 and x is going from 0 to 1, so why can't we write it this way? Well, the reason we can't write it this way is because that guy right there, this is a rectangle, right? If you're saying that x is going from 0 to 1 and y is going from 0 to 1, and there's no relationship between what x and y can be, you're talking about this rectangle. You're talking about this unit square. Right? That's the region you're talking about in that case. And that's clearly not what our region is. Our region is this fin. So we're not going to consider that. So that's not what this region looks like. So don't do it that way. If you want to switch the bounds, which we should do in this case, we should use this other approach, right? We should be using this way of defining our bounds because this will allow us to switch what x and y are. Let's see if this makes our lives any easier, and I think it will. This is the integral from 0 to 1, integral from x squared to 1. Same exact thing as before, just to be clear, I'm not just pulling something out of thin air. That's the same thing as the integral from 0 to 1 of the integral from 0 to root y. And I, for some reason, decided that it was going from x to, okay, I miswrote something here. There we go. From 0 to y of root y sine y dx dy. And what's this? This is the integral from 0 to 1 of root y times root y sine y dy. Or in other words, integral from 0 to 1 of y sine y dy. You still have to do that by parts. This is still an integral that you would have to do by parts, but it's a much easier integral to do than the one that we saw before. So now some of you might be a little bit rusty on integration by parts, so I am gonna do this one just so you can see what this looks like. So the idea basically is u is going to be something that's very easy to differentiate. Let's say u is y, so du is just dy. dv, something that's very easy to anti-differentiate. Let's say sine of y dy, which means v is negative cosine y. So this whole thing is going to become negative y cosine y plus, because you've already got the negative there, so that's u times v, minus v du, which in this case is plus cosine y dy, going from 0 to 1, integrated from 0 to 1. Which is going to be negative y cosine y from 0 to 1 plus sine y from 0 to 1, which is going to be negative cosine of 1 plus sine of 1. And that's about the best we can do, right? Sine of 1 minus cosine of 1. That's about the best that we can do. And that's fine. We've got our answer. We have exactly what we want this thing to be. So let's do another one. Let's say that we want to do, I don't know, the integral from 0 to 2 of the integral of y over 2 to 1 of y times cosine x cubed minus 1 dx dy. Well, once again, the issue here is going to be in this term, because the antiderivative of cosine x cubed minus 1 dx is very hard. It might even be impossible. And by the way, if a mathematician says that something is hard, they mean it. They really mean don't try this, because you're gonna hate yourself for doing it. So don't do that. What you want to do instead is anti-differentiate y times cosine. I guess I can include a y here. It doesn't really matter because y is a constant, but if you anti-differentiate x cubed minus 1 dy, well, that one's much easier. So let's do it that way. Once again, if we're going to do that, we need to switch the bounds of integration. We need to do that very carefully and conscientiously. So what do we know? We know that y is, we know that D, our region D in this case, are all points x and y, so that now y, we're told, is going from 0 to 2, and x, we're told, is going from 1/2 y to 1. That's what we know based on what the limits of integration are, right? We can, I'll color code this again so we can see what I'm getting at here, where the y terms are coming from, and also where the x terms are coming from. So what does that mean in terms of our region? Well, y is going from 0 to 2. So here's what y is. X, meanwhile, is going from 1/2 y to 1. So you want to think about the line y equals 2x, or x equals 1/2 y. And we know that x is going from 1/2 y up to 1. So this is the direction that x is going in, from 1/2 y to 1. So there's our region. That's the region we're interested in this case. So D can also be expressed, in other words, as all x and y, so that x is doing what? Well, x is going from 0 to 1. And y is doing what? Y is going from 0 to 2x in that case, right? How do I know that? Well, just look at this for a second, and we see that y is going from 0 upward to 2x. Right? Those lines are the exact same thing. So with that in mind, so now we can write what this double integral is. The iterated integral from 0 to 2 of the integral from y over 2 to 1, y cosine x cubed minus 1 dx dy. What's that? That's the integral from 0 to 1 of the integral from 0 to 2y, excuse me, not 2y, to x, y cosine x cubed minus 1 dy dx. Okay, so now we're going to now that's much easier to anti-differentiate. The integral of y, well, okay, that's just 1/2 y squared. So this becomes the integral of from 0 to 1 of 1/2 y squared cosine x cubed minus 1 from y equals 1, sorry, y equals 0 to y equals 2x dx. And that is just the integral from 0 to 1 of, let's see, y squared. Apply that to 2x. This becomes 2y squared, 2x squared cosine x cubed minus 1 dx. And that's just a basic u substitution. This you can write using u equals x cubed minus 1, and du is 3x squared dx. I always have to do that, by the way. I always have to write out what u and du are explicitly. So there's no shame in doing that, because I can now identify that that what this comes out to is the integral from now 0. This is -1. At 1, this is 0 of 2/3 cosine u du, or in other words, 2/3 times cosine of 0 minus cosine of -1. And by the way, cosine is an even function, so cosine of -1 is cosine of 1. So that's 2/3 of 1 minus cosine of 1. And that's our answer. And once again, that's about the best we can do. Okay. Actually, after looking at this, I'm realizing that I made a rather stupid mistake, which happens. Let me forget all this stuff. I made a rather silly error as I'm doing this, which I will fix right now. And here's the error. I forgot to actually anti-differentiate cosine. Whoopsie. So let's fix that. This is 2/3 sine of 0 minus sine of -1. Sine is an odd function, so this is not at all what I thought it was going to be. 2/3 sine of 1, since sine of 0 is 0. There we go. That's what I should have said in the first place. That fixes the issue. Okay, so let's do another example. But let's shift gears a little bit. We'll look at something a little different in the following way. So what if we want to look at the double integral over d of y squared over x squared plus y squared dA, and d is going to be the region between the circles, x squared plus y squared equals a squared, and x squared plus y squared equals b squared. Now, if we draw this out, we can see what this is. X squared plus y squared equals a squared. Let's say that this is a and this is b. This is going to be a not to scale figure, but this is not a graphic art class. and I am not a graphic artist, despite appearances. So here's what our region looks like. It's this washer between these circles. So how might we go about doing this? The fact that you've got this washer as the region we're integrating over, that very heavily suggests that this would be a good thing to do in polar coordinates. Oh, wait a second. Let me make this thicker again. So polar seems like a reasonable idea here. So let's say that D is the region r theta, so that r is between these numbers a and b. The radius is between a and b in this case, but theta can be anything. Theta, it can be any angle in the circle, so it's going from 0 to 2 pi. Now with that in mind, and because that's what D can look like, we should also probably identify what our function is. Y squared over x squared plus y squared, what would that become? That would be r squared sine squared theta over r squared. Or in other words, sine squared theta. So our double integral over D, y squared over x squared plus y squared dA, that's going to be the integral from 0 to 2 pi of the integral from a to b of sine squared theta r dr d, I nearly forgot the r there, r dr d theta, which is separable. You can write that as the integral from 0 to 2 pi sine squared theta d theta times the integral from a to b r dr. Now sine squared theta, this is one of these trig identities that we're really going to have at our fingertips, but I'll let you know what it is. 1 minus cosine 2 theta divided by 2. And this is an important trig identity, so we should have this at our fingertips as we're doing these exercises. Upshot, this becomes the integral from 0 to 2 pi of 1/2 1 minus cosine 2 theta d theta a to b r dr. Now these are much easier integrals to do, so these are going to become 1/2 r minus 1/4 sine 2 theta from 0 to 2 pi. And of course, that's theta in both cases, times 1/2 r squared from a to b. In other words, this whole thing is going to come out to pi over 2 times b squared minus a squared. And that's our final answer. Now, by the way, if you're, the more you do these, you might start to notice a pattern, because cosine of 2 theta, okay, that's going to antidifferentiate to sine theta. And if it antidifferentiates to sine theta and you're evaluating it at 0 and 2, okay, technically it antidifferentiates to sine of 2 theta, but it doesn't matter, because when you plug in 0 and 2 pi into it, you're going to get 0 either way. So that's just going to go to 0 after you antidifferentiate no matter what. So if you're, because these are the same thing. So the more you do these, you'll start to get used to that. And you'll see more and more examples of that phenomenon as the more of these we do. All right, others. Let's say that we want to look at, see if I can find an interesting looking one. So what if we have, here's a good one, integral from 0 to a of the integral from negative root a squared minus y squared root a squared minus y squared 2x plus y dx dy. Now the question is always going to become, how do we do that? How do we set this up? Now, if you were to try to do this directly, I'm not saying you can't do it directly, but you probably shouldn't. It's probably gonna cause you more pain and suffering than you necessarily want. So this would be the integral from from 0 to a. And let's see, you're anti-differentiating with respect to x. So this is going to become x squared plus xy from x equals negative root a squared minus y squared to x equals root a squared minus y squared dy. Already, this is beginning to look a little bit obnoxious. Oops. I keep on switching a and 0 for some strange reason. A squared minus y squared plus y root a squared minus y squared minus a squared plus y squared and then plus root a squared minus y squared. Oh, I guess it's not that bad. I was wrong. So you could do this directly, because those would cancel. Oh, I left out a y term, my mistake. I keep doing that. Integral from 0 to a of 2y root a squared minus y squared dy, which would give us 2/3, or negative 2/3, a squared minus y squared to the 3/2, evaluated from y equals 0 to y equals a, which would, in other words, be 2/3 a cubed. So I guess you can do it directly. I was wrong. But it's not the only approach. Let's see if we can use a different strategy, because you can also do this using polar coordinates in the following way. So then let's see if we get the same answer. So y is going from 0 to a. We know that. And x is going from, and x, we're told, is going from negative a squared minus y squared to positive root a squared minus y squared. Or in other words, so here's the lower limit for what y can be. Here's the upper limit for what y can be. And x, here's negative a, and here's positive a. X is going from negative root a squared minus y squared, or in other words, x squared equals a squared minus y squared. Or in other words, x squared plus y squared equals a squared. So basically, here's our region. It's this half circle. So the integral that we want from, I keep on doing that. The integral that we want from 0 to a, negative root a squared minus y squared, positive root a squared minus y squared, 2x plus y dx dy. In polar coordinates, this would become the integral from 0 to pi, integral from 0 to a, 2r cosine theta plus r sine theta, r d theta. Or in other words, you could separate this, 0 to pi, 2 cosine theta plus sine of theta, d theta, times integral from 0 to a of, in this case, this would be r squared dr. Now again, the 2 cosine theta, that's going to vanish because that's because the integral of cosine theta d theta is sine theta, and we're evaluating it at 0 and pi, so that's going to go away. So we're going to be left with negative cosine pi plus cosine 0 times 1/3 a cubed. Or in other words, 2/3 a cubed. Well, how about that? So these are two different ways of going about it. Whichever way you want to use, it's up to you. My general advice is to set it up in as many ways as you can and choose for yourself which one is going to you think is going to make the most sense. This one happened to work out nicely because the integrand was relatively easy to begin with, but often polar coordinates can be easier to work in. So so my general advice is to just try to set it up in as many different ways as possible. Usually that's the best strategy. So let's see. I want to do one more in the time I have left. Let's say that we want to find the double integral over d of the function of just the function x dA. And in this case, we're going to say that d is the region between, it's going to be the region between the circles x squared plus y squared equals 4, and x squared plus y squared equals 2x. Now, what do those look like, by the way? X squared plus y squared equals 4. So again, we should always try drawing this so we can figure out what the best strategy is going to be. X squared plus y squared equals 4. That's just a circle of radius 2. So that's not terrible. So we've got a circle of radius 2. But meanwhile, the fact that we have x squared plus y squared equals 2x, so know that it's not a circle of varying radius. There's no such thing as that. But this is going to become x squared minus 2x plus y squared equals 0. Or after completing the square, x squared minus 2x plus 1 plus y squared equals 0, or x minus 1 squared plus y squared equals 1. Uh-oh, I left out, I made a small mistake there. So x minus 1, so so here's your new center. Let me color this in orange. So you've got your center at 1. Your radius is you've got a radius of 1. So there's your other circle, and it's the region between those things. So in other words, here's the region we're interested in. It's this whole thing over here, right? This this disk with a hole in the side punched out of it. So that's the region we're interested in. Now, there's a little bit of a challenge here. The challenge here is actually figuring out how to describe D. How are we going to describe D in this case? There's the, that's part of the challenge. So there are a couple ways you can go about doing this. One thing that we can try is breaking this up into two different regions. One of them is going to be this left side, this left half circle. The other one is going to be on the right. Let's see where that takes us. Let's think about this for a little bit. Now, here's what we can do. Ultimately, what we want to be able to say is that D is, let me get a bit older. We want to be able to say that D is something in polar coordinates. Now, theta is going to be going all the way around. So probably theta is going to be going from 0 to 2 pi. But what about r? Now for r, what we can do is we can observe that we've got all of these line segments going from the origin outward to the edge of the circle. So the question we should be asking ourselves is, okay, well, as it's doing that, what curves is it between? Because this is the piece of r that we really care about, right? It's the piece between these curves. So what curves is it hitting? And as soon as we're bolding that, we can begin to see the answer to that question. Actually, okay, so I need to back up and change some of my story here. No, that part was okay. So that part's fine. So that is what that piece of it is. However, the image is not quite right. And the reason the image is not quite right is because I left out an important detail in the setup of this problem that I should include. And that detail that I left out is the region in the first quadrant. I skipped over that part as I was reading this problem, and that makes this much easier in terms of actually doing this, because otherwise you'd have to have done 2 different regions, like I was beginning to say, and that would be cruddy. So let's try this again. So okay, 1, 2, 1, 2. Again, we still have the circle, a bit of a weird circle, but we still have the circle x squared plus y squared equals equals 4. And we have the circle on the inside, which is x squared, which is x minus 1 squared plus y squared equals 1. But we're interested now in the region between these things, in the first quadrant. That's going to make a huge difference. Now, once again, we still want to be able to figure out, okay, well, you've got a line segment going from the origin outward to some other point on the curve. The question is, how much of that region is actually inside the curve itself? You see what I'm trying to illustrate here is, as we're doing this, drawing these line segments, what we're trying to figure out is how much of that line segment is actually inside the region, because however much is inside the region, that's the part that we're trying to integrate. Right, so this is the segment we actually care about. So really what the question is going to come down to is, okay, well, what the heck is this curve? Is there a better way we can describe, that object? Well, if we have that x squared plus y squared equals 2x, that's the same thing as saying r squared equals 2r cosine theta, right? Or in other words, r equals 2 cosine theta. Aha! So in other words, this circle down, this curve down here, let me draw it this way. This bottom curve in the region that is r equals 2 cosine theta. And r is going to be between that object and, I can do this, and this one, this top curve on the exterior. And that top curve is just r equals 2. So now we can actually say what this region is. We can say in this case that D, so all of this is to say that D are all points r in theta, so that theta, what's theta going between? Theta is starting at 0, but going all the way, it's in the first quadrant, so it's going all the way up to pi over 2. R, meanwhile, is going from 2 cosine theta to 2. Right? From the light blue curve to the magenta curve. So now we're basically ready to figure out what our integral is. X dA. The bounds are going to be from 0 to pi over 2, from 2 cosine theta to 2, of r cosine theta dr d theta. And for those of you here who are paying very close attention, you'll notice that I made a mistake here, quite deliberately. And the mistake that I made was I left out an extra factor of r. So you have to make sure that you include your extra r dr d theta. So this becomes the integral from 0 to pi over 2, r squared cosine theta dr d theta. Now you can't separate this because you've, I left out something very important here. I left out one of the integrals. That's no good. 2 cosine theta to 2, r squared cosine theta dr d theta. Now, you anti-differentiate this, pi over 2, and this becomes 1/3 of 2 cosine theta cubed cosine theta d theta, integral from 0 to pi over 2 of 8/3 cosine to the 4th theta d theta, cosine to the 4th. Now, that's kind of frustrating in some ways because, well, hold on a second, how would you go about doing that? We know we have a cosine squared identity, but we don't have a cosine to the 4th identity. But we can use our cosine squared identity. Remember that cosine squared of theta is 1/2 1 plus cosine 2 theta. And you can use that here to write this as the integral from 0 to pi over 2. Still have the 8/3, that's not changing, of 1/4 1 plus cosine 2 theta squared d theta. Clean that up a little bit algebraically. That becomes 0 to pi over 2 of 2/3 1 plus cosine 2 theta squared. Still not great because you still got an extra square term in there, but that's okay. You can undo that. 0 to pi over 2, 2/3 1 plus 2 cosine 2 theta plus cosine squared 2 theta. And then you can apply that identity again. So this becomes the integral from 0 to pi over 2 of 2/3 plus 4/3 cosine 2 theta, that's just distribution, plus 1/3, because you're dividing it by 2, 1/3 1 plus cosine 4 theta, because you multiply what's inside of theta by another factor of 2, d theta. And that's much easier to do. That's just a whole bunch of basic trig integrals of just cosine and u substitution. That's not very difficult at all. So I'll leave it to you to work out the details, but I'll let you know that this integral is just going to eventually should just eventually come out to 16 minus 3 pi over 6 after doing some algebra. All right, so we'll leave us there. Thank you, everyone. So I hope that this has been helpful, and I will talk to you guys on next week, because I'm doing the recitation next week. So thank you, everyone. Bye-bye.